In the first fraction of a second after the Big Bang, the universe was a chaotic, ultra-dense plasma. As that immense heat dissipated, the cosmos cooled and structurally snapped into place, establishing the physical laws we observe today. The foundation of those laws rests on the quantum vacuum. In modern quantum field theory, the vacuum is not empty space. It is the absolute lowest possible energy state of an intricate, ubiquitous web of interacting quantum fields. This baseline state operates as the universe's operating system. It establishes the resting masses of all elementary particles, the behavior of the fundamental forces, and the precise values of the constants of nature. However, data from modern particle physics presents a severe mathematical anomaly. Calculations indicate that our specific universe does not currently reside in the absolute lowest possible energy state. This plot maps the measured mass of the Higgs boson on the x-axis against the top quark on the y-axis. Weighing the Higgs at 125 giga-electron-volts against the top quark at 173 giga-electron-volts, their intersection lands squarely inside a zone labeled metastable. Because of this specific mass ratio, the physical reality we experience is trapped in a localized energy valley. The fundamental laws of physics as currently constructed are merely a transient phase in the deep time evolution of the cosmos. In classical physics, a system trapped within a local energy minimum is strictly stable. Unless external thermal or kinetic energy is injected to push the system over the surrounding barrier, it will remain there indefinitely. Quantum mechanics bypasses this thermal requirement entirely. Even at absolute zero, a quantum field can spontaneously tunnel straight through the potential barrier, transitioning from a higher energy state into a lower energy state. This catastrophic transition is known as false vacuum decay. It is a first-order phase transition, characterized by the spontaneous, stochastic nucleation of expanding bubbles of true vacuum within the pre-existing background space. The ultimate thermodynamic fate of the cosmos is not an abstract mystery. It is a rigorously modeled process governed by strict semi-classical mechanics and fluid hydrodynamics. This graph represents the Higgs field's scalar potential. On the left is the local minimum, the false vacuum. A deeper true vacuum exists, separated by a massive energy barrier. To reach it, the field must undergo quantum tunneling, cutting directly through the barrier. The formal math required to calculate the exact probability of this tunneling was pioneered by physicist Sidney Coleman in 1977. Coleman solved the equations by analytically continuing standard time into imaginary time, effectively mapping the complex oscillatory path into a decaying exponential. Within this framework, Coleman identified a unique finite action mathematical trajectory called the bounce or instanton. This specific field configuration represents the path of least resistance for a field transitioning out of the false vacuum and bouncing back. The probability of this transition occurring is exponentially suppressed by a value called the Euclidean action. The Euclidean action is essentially the aggregate physical penalty derived from the immense height and width of the energy barrier. Because the decay rate is exquisitely sensitive to the precise shape of this barrier, any microscopic change to the input masses of our fundamental forces vastly alters the statistical lifespan of the universe. To evaluate these trajectories, Coleman developed the thin wall approximation. A true vacuum bubble forms a sharp boundary, the domain wall. Its survival is a hydrodynamic competition. The lower energy interior exerts immense outward pressure, while the domain wall's high energy surface tension forces the bubble to collapse inward. This creates a strict critical radius threshold. Bubbles that nucleate too small are immediately crushed out of existence by their own surface tension. Only bubbles that form at or above the critical radius are pushed by the volume energy into continuous expansion. The terminal velocity of a surviving bubble depends on the density of the surrounding thermal plasma. High friction results in a subsonic expansion called a deflagration. If the driving force overcomes the friction, the wall velocity surpasses the speed of sound, transitioning into an ultra-relativistic runaway detonation. The destruction of a metastable universe relies on satisfying this hydrodynamic threshold. A quantum spark alone is insufficient. The bubble must be large enough to ignite a runaway detonation that accelerates towards the speed of light. To understand why our specific universe is prone to this decay, we have to look closely at the Higgs field. In classical, tree-level mathematics, the Higgs potential appears perfectly stable, mapping out a bounded Mexican hat shape. But classical math is insufficient. Quantum field theory dictates that the Higgs potential is constantly modified by quantum loop corrections, the aggregate interactions of all other standard model particles coupling to the Higgs field at varying energy scales. This line graph maps the energy scale dependence of the Higgs field using the renormalization group equations. These equations describe a high-stakes mathematical tug-of-war. Massive bosons pull the self-coupling parameter upward towards stability, while fermions drag the parameter downward towards instability. The exact weight of those particles has been determined through high-precision collision data gathered at facilities like the Large Hadron Collider. Because a fermion's coupling strength is directly proportional to its mass, the top quark dictates the entire trajectory. Weighing in at roughly 173 giga-electron volts, it is by far the heaviest elementary particle, exerting an overwhelming negative pull on the Higgs self-coupling parameter. Here, we see the consequence of that weight. At ultra-high energies, the top quark's negative pull completely overpowers the positive bosonic contributions. The self-coupling parameter inevitably crosses zero and becomes negative at an instability scale around 10 to the power of 10 giga-electron volts. When that parameter drops below zero, the effective potential of the Higgs field turns over and plummets. The physical weight of the top quark proves the stability of the electroweak vacuum is broken. Observing a cosmological false vacuum decay event directly is impossible. However, the precise thermodynamic and quantum mechanics governing the phenomenon can be simulated and tested in tabletop analog models. This diagram shows the 2024 Trento experiment. Researchers trapped an ultra-cooled cloud of sodium-23 to create a ferromagnetic superfluid. By manipulating magnetic fields, they emulated the Higgs field, deforming the energy landscape into a double-well potential and trapping the atoms in an artificial false vacuum. The system was held at less than a microkelvin above absolute zero. Eventually, ambient thermal fluctuations provided the exact activation energy required for the atoms to overcome the engineered potential barrier. The team directly observed the spontaneous nucleation of spatially localized spin bubbles. Inside these physical bubbles, the atoms had successfully transitioned into the true vacuum configuration. This experiment confirmed that Sidney Coleman's abstract, semi-classical bounce mechanics accurately dictate physical reality at the macroscopic laboratory level. While the math of false vacuum decay is sound, the tunneling probability in our actual universe is exquisitely small. The sheer height and width of the Standard Model's potential energy barrier results in a massive Euclidean action, severely restricting the likelihood of a decay event. This logarithmic timeline compares the current age of the universe against a highly scrutinized 2024 revision of the vacuum's expected lifetime. The updated calculations established a statistical cosmological lifespan of 10 to the power of 790 years. By contrast, the consensus for the heat death of the universe, where star formation ceases and thermodynamic energy approaches absolute zero, will occur trillions of years prior. Thermodynamic exhaustion will freeze the cosmos long before a decay bubble is statistically likely to nucleate. Consequently, theoretical physicists do not view vacuum metastability as an apocalyptic warning. Instead, it serves as a glaring indicator that the Standard Model is incomplete. Theories exploring physics beyond the Standard Model, such as supersymmetry, offer immediate stabilization. Supersymmetry introduces new superpartners for every existing particle, such as scalar top quarks or squarks. These additional bosonic degrees of freedom would inject massive positive values into the renormalization group equations, actively preventing the potential from ever turning negative. Until a grand unified theory is proven, the prediction of a false vacuum stands as theoretical physics' most rigorous compass. It highlights the exact limitations of our current math, driving the search for the true, stable bedrock of reality.